Thanks everybody for coming. My name is Thiago Macieria. I'm software engineer, software architect at Intel. I've got this session for you guys here talking about IPv6, something I would have hoped that by 2016 it would have been common knowledge. Turns out it isn't. This is why I'm here. And you'll see why actually IPv6 is very important for embedded devices. It's actually at the very end of the session, but we'll get there. Just a couple of notes before. The slides will be available online after the session, so you don't have to take pictures unless you want to. I'm not very photogenic, but you're welcome to take pictures of me too. There will be a video, so I will try to repeat any questions, but if you can, or you can also just come into the microphone at the center of the room and ask your questions when we are in the Q&A part. By way of introducing myself, this is apparently me in the pre-ages of internet and contributing to IPv6 in 1999 with a typewriter. No, not really. So I started actually contributing to open source with IPv6. I had one or two patches before to minor things, but it was only because when I wanted an IPv6 capable browser in 1999 and 2000 that I actually began contributing to open source. So you can see, by the way, how far back IPv6 goes. It actually goes back onto 1995, the first IPv6 RFC published. It actually even goes back a little before that when IPNG task force was created in IETF, was 1993. So we're talking 23 years ago that they started thinking that IPv4 would run out. There were changes to IPv4 that actually helped mitigate those problems. That's why the internet has not crashed and burned. Just again, to introduce myself, I began contributing to IPv6, which led me to, actually the browser I was contributing to was Conqueror at the time, the KDE2 browser. That led me to become a KDE developer, which led me to become a Qt developer, and that led in turn for me getting hired at Intel. My job today at Intel is working on Internet of Things. So it's interesting when I started working on Internet of Things 2 years back, that, hey, I'm going back to my roots and talking about IPv6 and convincing people in the projects I was working on that IPv6 was actually important. And I was quite surprised when we started working on the IoTivity project that the developers did not know how to do IPv6. It's not that they didn't think it was important. They did think it was important. They just did not know how to do it. This is why I'm here. So, let's talk about the IPv4 exhaustion. When is the Internet Assigned Numbers Authority, IANA, going to run out of IPv4 blocks it can assign? Let's see a show of hands. Who thinks it's 2016 or later? Okay, apparently you guys know the answer. It has happened. It has already happened. It was in 2011 that the Internet Assigned Numbers Authority ran out of blocks. The first one to run out, the first local registry to run out was the Asia one. Just a couple of months into 2011, they ran out. Followed by Europe, followed by Latin America, followed by last year in 2015, the North American local registry. So if you need a new block and you don't want to horse trade it with another company by buying and selling or going on a wait list, the only place you can do that is in Africa. This is where we are today. This is how far we've allowed us to go without IPv6, that we have this problem today. So I divided my presentation into a brief overview of IPv6. I'm guessing that since Most hands did not go up here on when I presented that challenge. You are familiar with it, I'll go a little faster. Then I'm going to talk about API, which is what I wanted people to get. Why is it so simple? Now, I'm going to talk about C API, because we're at the Embedded Linux Conference in OpenIoT, but it's important to understand that most other languages have it, and interestingly, most other languages actually have support for it natively. And then I'm going to talk about a couple of things you can do with IPv6 that you can't with IPv4. So before that, let's address the big elephant in the room. What happened to IPv5? What is this here? No, not a spaceship, it's a space station. Huh? No, this is Babylon 4. Not Babylon 5, it's Babylon 4. If you remember the show's history, why is it called Babylon 5? Because Babylon 1, 2, and 3 were sabotaged and exploded, and Babylon 4 disappeared. So what happened to IPv5? IPv5 actually, the history goes like this. TCP version 0 was the common protocol. It split, and version 1, IP version 1, 2, and 3 were development protocols. V4 is the one that we're using today. V5, the number 5 in the header protocol, was used for a different protocol called IP streams, which went nowhere. So when the IP Next Generation work group started working on this, the first number they had available was 6, which is why we're talking IPv6. So a couple of comparison details with V4. Address size, as many of you probably know, has expanded from 32 bits to 128. Which is a lot more. Apparently my notes are gone, where I had the number of IP addresses per square centimeter of Earth. I don't have the number now because they disappeared. But interestingly, some of the things that came with IPv6 became interesting for IPv4 as well. So multicasting, as an example. For IP version 4, multicasting is actually optional on IP stacks. They don't have to implement it. And probably the idea was it's expensive, it's difficult to do it, and difficult to implement it with a given network functionality, the network radios and connections at the time. So it was optional. IPv6 actually makes it mandatory for a number of good reasons, including that it actually needs it for the address resolution, which is itself. So in order to, for example, to translate an IP to a MAC address, this is how it works. How am I going to transmit a packet to somebody? It uses itself, and it does that by using multicast. So it's a chicken and the egg interesting solution. I'm not going to go into the details. I can explain to whoever wants it later. Another interesting one was the increase of the minimum maximum transmit unit, the MTU. The MTU is the size of the packet that is allowed to go through, and you know it's going to go through without getting fragmented or dropped along the way because it was too big. 68 octets isn't a lot. I mean, you can do a DNS query, and if the answer is very simple, you probably fit. But beyond that, you have a problem, which means that fragmentation was actually done by routers. And so along the way, your packet could get fragmented by routers and arrive in pieces at the destination. IPv6, that does something different. It says, well, the minimum is 1280. So for network radio technologies like 802.15.4 that have a frame size of 128, what they need to do is that the radio layer needs to do the fragmenting before it gets to the next hop, the next node, and then it reassembles, and then the IP stack will see it. This allows protocols, again, like DNS, to say, actually, I can use 1,024 bytes on my payloads. I don't have to be limited and have to have workarounds for when the packets get dropped. So DNS on version 4, for example, it has this workaround of if the response came fragmented, didn't arrive, it will actually go into TCP, which is a lot more expensive, to get the same answer. So by increasing the packet size, we're guaranteed that actually can do useful things without being feared, without having the fear that the packet will not get through. I mean, of course, we all know network technologies may not actually go through. if fragmentation is necessary, if I'm sending a bigger packet, the origin will do it. This simplifies routers. So, and interestingly, what happens is that IPv6 made routers simpler. Yes, the address size is bigger. Yes, you cannot do a simple 32-bit comparison with a register because it's now bigger. But it actually made routing and routers easier. I mean, the maximum packet size, they were thinking ahead. Like 640 kilobytes will be enough for everybody. We know it isn't. So they were thinking ahead of time. Another interesting one was privacy extension. So when IPv6 came along, they started to think about those things. So IPsec, which many of you have heard and is used by VPNs today, came out of IPv6. I'm going to show more interesting things that IPv6 can do that IPv4 cannot, that are related to privacy. And this is because they started with this in the beginning. And you have a much bigger address space, so you can actually play around with the bits. So another example of things that came along from IPv6 into IPv4 is link local addresses. How many of you have seen this 169 to 64 address in your computers before? Usually, what does that mean? Sorry, I couldn't hear. You can't get an address, which means that you're probably out of the internet. Whenever you see this, you're like, damn it, couldn't get an address. And if you're here in the conference, where you know everybody here has 3 or 4 devices connected to the Wi-Fi, the DHCP server doesn't know, like, damn it, I couldn't get an IP address, let me reconnect. This is what it means to you today, right? IPv6 is not the same. Another one is anycasting. I'll show again anycasting a bit later. So it looks like a regular address, but it means that it might actually reach different destinations. This came out of IPv6. And like I said, IPsec. I'll go back to the link local addresses in a minute. So what does an IPv6 address look like? 128 bits, can be compressed. It can be compressed further from this RFC that I found. When I was writing the presentation on Friday, I realized, I work on Qt, right, that we didn't have RFC 1924 support in Qt, so I decided to write it. And where's my, here? So I decided to write support for it. There's actually a commit that I made on Friday to add support to it. Sorry if you may not be able to see it all the way there in the back. So I just wrote the code to do base 85 compression. And here's actually the unit test. And you can see I've got an IP address there, the same one working. Guys, what day was Friday? Okay, I'm just joking. So this was my April Fool's joke for the Qt project, and apparently I got people because I've got the approval for the commit. The commit message is pretty good, like I'm talking about, and this other one, and if you look at the previous commit, which is real, I had a commit talking about the other RFC, and this is why I got people. Anyway, back to the presentation. Localhost and any host are actually simpler to do. So you don't have to remember 127.0.0.1. It's just 1 and 0, right? So the compressed form just takes a bunch of sequential zeros, as you saw on the previous slide as well. You take a bunch of zeros in sequence and replace them with a double column. Now, I'm not expecting anybody to actually remember those addresses. That's why we have DNS for. Nobody will need to type IP addresses anymore. We usually don't. We just copy-paste. It's very seldom that people remember IP addresses. So let's talk about those link local addresses. And the interesting thing, one of the most important things that IPv6 came along with is called the stateless address auto-configuration. What does that mean? It means that each node in the network can auto-configure its address, that means independent of anybody else, configure its address, without having its state have to be remembered elsewhere. There's no state on the router, there's no state on the local host. Think about it. DHCP is stateful. It means there's a transaction. There's a question, can I have an address? Yes, you can have an address. Here's an address. Okay, I'll take that address. So yeah, it's a four-step handshake. So on networks without DHCP servers, it simply auto-configures its address. So when you see the address for link local in IPv6, which starts with FE80, it doesn't mean you're out of the internet. It just means I'm already configured. More than that, if it finds a router present, I'm not talking about the DHCP server, it finds a router present, it will configure even global addresses. So now I don't need to have a DHCP server in my network. I can have a DHCP server in my network. So the DHCP server can be queried, again, statelessly, for extra information. What is my DNS server? What is my NTP server? What is my Windows SMB network server? So you can query for extra information statelessly. There's no transaction on DHCP. Or you can get the address from DHCP transactionally as well, statefully. But the interesting thing is if the router is present and it's announcing itself, it's called IPv6 router announcement. I will get that information, I'll get the prefixes, and automatically I am on the internet. Here's how it works. I take my MAC address of my machine. This is not the MAC address of my machine. I'll take one MAC address. I'll create an extended version called EUI64, which just inserts 2 bytes in the middle. Flip 1 bit and change it into the IPv6 interface identifier. That bit there is just the universal or local bit on MAC addresses. It indicates whether this is universally assigned or not. The 3 bytes in the beginning of the MAC address are assigned to a specific organization, but they never have the number 2 there. The bit is never there. That indicates that it's a global number. And then what I do is that I append it with my link local prefix and produce my link local address. Or if I get more information from the router, which I just said before, I will take that and produce one single address. So you can see this is a global address. Without the router having to know I'm there, it just sent a packet because that's what it does. I automatically configured my address. I'm online, period. Questions here?
So what would happen if someone else on your network spoofed their MAC address?
So what would happen if you had somebody with the same address for whatever reason, legitimately or not? In the process, which I didn't describe here, there is the duplicate address detection. It's DAD, the duplicate address detection. So what it does is that it sends a packet saying who's there with this address. If nobody answers, that means I am it. If somebody answered like, okay, I'll try something else. I'll get to that, something else in a second. There was another question? Same one, yes. How do you get the default gateway? The router that sent the router announcement is your default gateway, right? There's a bit in the router announcement protocol says, I am a gateway, and you can trust me, you can set the route for it. You can send a router announcement without that bit saying, I'm just announcing prefixes. Usually what that happens is that the packet gets ignored. I've never seen it used that way.
What about
Multi-homing and multipath. That's a very good question. What would happen there? You probably would have 2 routers announcing, right? 2 different prefixes. Or even the same prefix. You might have the same prefix getting announced. And what would happen is your host would figure out, I have 2 routers for the same prefix, and I would configure 2 routes, which is multi-homing. I actually have never tested that particular thing. I don't know how Linux would react, but it's an interesting thing to test. Nobody asked the question I wanted. What happens to my privacy? Because now I've got this fixed address that is getting everywhere. Like every network I connect to, I have the same interface identifier, right? Which would allow somebody to track me wherever I am. No, well, the guys thought about it. So what happens is that they have two different and complementary solutions for that. The first is called temporary addresses. It's a little older. It's been in operation for a long time. What happens simply is that you tell Linux or whatever OS you are in that I want a temporary address. And what it does, instead of taking my MAC address, it generates a random one, does the duplicate address detection just to make sure there's nobody there, right? And if nobody's there, I'll take it for a fixed period of time, like a day, half a day. And then we'll do it and redo it again. So here's an interesting, that's what I said, that the expanded address space allows me to do interesting things. I can just put a random number in that address field. So it's rotated after a time, so my existing connections will continue to work. I'll just add a new one, and every new outgoing connection will use that. The new interesting one is the stable but opaque address. So what it does is that it suggests using a function like SHA-1, which is pseudo-random, that you put in input like that you have a passphrase, a password, just something that you chose yourself, concatenate with the network address or the wireless SSID and put a couple of other information there, run it through SHA-1 and take the 64 bits of it, which means that it changes very often, but it's stable. So if you connect to the same network twice, you get to the same address, which means that if you had any assigned resources to you, you would get them back. It wouldn't be random. That's why they said they are complementary. I would use this one, the stable but opaque, to get incoming connections. I have my address in this network. Think of, for example, no, it's a bad example because we do not need port forwarding. But imagine that I actually asked the firewall to poke a hole for me, right? So there is an incoming packet. There's no address translation, but there's an incoming packet on the firewall for me. I would keep getting that without having to ask and re-ask. But any outgoing packets would come this way, so you can't tell who it is actually. More than that, because this actually makes the link local address change, not even the routers in that network or anybody else in that network can detect me if I change networks again. You can't follow me.
Are IPv6 addresses expected to be unique globally?
Our IP address is expected to be unique globally.
So when you are trying to figure out if someone else has your address, don't you theoretically have to wait for everyone in the world?
Don't you have to wait for everybody in the world? So what you do is you split the network, right? Half of the address, this is the 64 here, right? This is the prefix that I got from my provider.
Right.
So there's an extension to the HCP called prefix delegation. I ask my provider for an IP block. I get an entire network out of it. And then from that block, I know it's global because it's actually hierarchically assigned. So the IANA gave to Aaron in in North America, gave a block. That block got subdelegated to, in my case, Comcast. Comcast gives me a network prefix of 64. And then inside that network, I'm inside one network. So I don't need to wait for the entire world. I just wait for locally, right? The timing depends on, of course, your radio protocol or wired protocol. So, but it's in the order of a second or two. It's very quick. So you don't have to wait globally because the address is split in two. That's another interesting thing that you just reminded me. So every network in IPv6 usually starts with a 64-bit prefix. So I can put 2 to the 64 devices in that network if I so wanted. Of course, I'm going to overload the network before we get into that level. We're not going to get 2 to the 64 devices connected to a network. But on the other hand, we have 2 to the 64-bit networks possible. That's the square of how many IP addresses we had in IPv4. So networks possible in IPv6 is the square of what we had in IPv4. And they assigned, I think, 0.03125% of the addresses to the world. The rest is reserved for the future. Yeah. So I talked about the casts, right? Unicast is the one everybody knows. I have my source, I have my destination, I reach it. It's one-to-one. The multicast, which I mentioned before, is one to many, in the sense of one to everybody in a particular group. So there's a group created. I'm not going to get into details on how it's created, but there's a group created, everybody subscribed to it. When I send a packet to the group, everybody receives it. As you can see, there's somebody left out because that one isn't part of the group. Now, the anycast, which is the interesting one, is one to any of the group. Any of those in the group could receive it. I'll send it to the group, and one of them will receive it. Doesn't matter which one. So a typical anycast group you would find in a network, if it were set up, is the address 0 on that network, which is the router. I don't need to figure out what the address of the router is, and I don't need to figure out the multi-homing. I'll send it to the anycast. Any of them will pick it up and follow up. Now you can see it doesn't differ from the generic address, right? So my host doesn't know it's sending to anycast, it's just sending. It doesn't know the difference. On multicast, there's a little difference. So you can see the address is a little different. FF means multicast, whereas the global addresses start with 2 or 3. That's where the 0.03, yeah, it's 1/8 of the possibilities, which isn't 0.012, yeah. I calculated it wrong. Questions here? Let's talk about, okay, go ahead. What makes it become anycast if it just looks the same? Well, if you're in a local network, that means the duplicate address resolution was suspended. All the hosts that do know about anycasting need to suspend disbelief, right? They need to suspend the duplicate address resolution because they know that there is somebody else in that address. So whenever you send the packet, it will be received by all of them. If you're doing this with global addresses, and this is where it becomes also very interesting, is it's now a routing problem. So this particular address is announced as routable from different networks. So you're basically doing anycast routing over the internet. So if I want to find a gateway out of my company network, well, the routers along the way know that I can go via A or via B, doesn't matter. So the routing protocols, which are out of scope here, would decide it. IPv6 would be only caring about the local network, which is suspend the duplicate address detection. Now, we can assign as many as we want to it. When I ask who has this address, remember, we're not using ARP anymore. We're using IPv6, ICMP. I can ask who has this. I'll get multiple answers. I can send to any of them. Did what answer?
And that's how you define the group.
That's how we found.
That's the definition of that anycast group. Is everyone responds.
Yes, that's how. So that is the definition of anycast group locally on a local network. Is I suspended the duplicate address detection. When I ask for anybody who has this IP address, which MAC address has this IP address, we get multiple answers. That's different from multicasting. Multicasting actually requires that the network, the level 1, support multicasting, which means that I'm not sending, there's a specific MAC address assigned to this group, which is nothing but, the last 32 bits, the last 24 bits of the address, the group address, plus a prefix that is assigned globally by the MAC authority saying this is multicast for IPv6. So I send to that. I know that the hosts that are interested in this will have the MAC address turned on and will receive it. Actually, I can and probably should just flip to a shell and show you. Where do I have my shell? No, that's not it. Here. Where did it go? Okay. So here's what happened. I have this, by the way, this is the multicast address printing out. So I have my group, right? And you can see that I have an IP address, a MAC address that matches it, right? When I have the MAC address, by the way, the 1 indicates multicast and the 2 is global. It will just assign this MAC address. So whenever I send a packet to this multicast address, it will send on this MAC address. And then whenever somebody else is sending, I will receive it because my wireless card here in this case has the confirmation that it will be receiving on all of those. Such a thing also exists for IPv4. So the 251 here is this guy here. And you can see it's actually the same group ID. That's because that's MDNS. So MDNS address on IPv4 is this, on IPv6 is this, and they share the same group ID, not a coincidence. Okay, so any other questions before I go into API?
So then they overlap, both IPv4 and IPv6 overlap the MAC addresses in your frame?
So do IPv4 and IPv6 MAC addresses overlap? No, they don't, because the prefix is different. So I'm using 3333 for IPv6, and I'm using 01005E for v4. So the prefix is different, but the group ID is actually the same and not a coincidence. Anything else? Okay, so let's talk about API. What you need to know. Don't assume anything about the address. Don't try to construct, don't try to just assume it's an opaque thing. Use the high-level API that you have, if you have it. So if you're using a tool, like I'm a Qt developer, right? Just use the Qt functionality for this. It's IPv6 enabled, has been since 2001. If you're using libcurl, use the libcurl functionality. Do not try to invent your things. Of course, this session is actually about how if you want to invent your own code, but that's fine. So what if you do? Now, use the IPv6 API, always. Do not forget the IPv4 one. Just use the IPv6 one. For 2 reasons. First, because they support IPv4. The API will give you v4 addresses when the time comes. And second, because even if you do have an IPv6 socket, it will talk to IPv4. More on that on 2 slides. Anything that you have an API, and by the way, do this for me. If you find any API without IPv6 support in 2016, send it to the garbage bin. Send it to the developer saying, this is unacceptable, please give me IPv6 support, and stop using it until they do. So as an example of why not to create your own code to do things, use what exists. So here's a URL. Everybody knows what a URL is, I'm hoping. And I'm asking you to put that IPv6 address in that URL. Anybody see a problem? Colons. Exactly. You need a square bracket. This is what an IPv6 URL looks like. So this is just an example. Don't try to construct things by hand and assuming that you know. Use the API for it. So if you're using Qt, there's QRL, and I spent a lot of time making it work. So let's look at the basic socket API. I'm sorry, I don't think everybody in the back is going to be able to read this. Don't worry too much. This is the sockadder struct. I copied out of the Linux headers. A socket address contains the port number and the address, which is the same on IPv6. Port number and the address, which just happens to be bigger. They put a number 6 in everything there. And the family number, which says v4 or v6. There are 2 extra fields. The scope ID is only used when you're doing link local because you need to identify which link it is. Remember, multi-home, but also multiple network interfaces. I need to choose which one I want to send on. The flow info, I've never used. It's been there forever, and I've never seen it used. If you need to put those on an existing struct, for example, the recommendation is to use the sock address storage, which is big enough for all of your addresses, v4, v6, and probably anything in the future, including, by the way, Unix sockets. So this is what you need when you're writing the code. Just put it there and then do necessary casting, or put them in a union. A very common use of this, very common way of doing this is to create a union with sock address in for Internet by IPv4, in6, storage, and if necessary, Unix. Just put them in a union, and you can access the same family one, which is always the beginning of all of them, in any of them. And if it says AF inet 6, I know which one it is. If it says AF Unix, I know which one it is. Right? So it's a way of doing variance with your addresses. But most of the time, you should not be using this. I showed you this just to show it's actually very similar. You should not be scared of this. What you should be using is getAddrInfo. Do not use getHost by name anymore. Please don't. Forget. No more getHost by name. You want getAddrInfo. You probably will see better when you get the slides. You set up a hints file. Actually, I can show these. I can show, where is the code? Here, much bigger. So what you will do is you set the hints saying, I want any address family. I'm okay with v4, v6. You can say I want only v4, but I'm saying I want v4 and v6. Do not return v6 if I don't have v6 on my machine. So addrconfig, that allows me to skip one DNS probe. I'm asking for the host canonical name. This is optional, just because of the example. If you were doing bind, for example, you would add the flag of passive, and I'm asking for TCP, so sock strings. I'll ask for it, and here's an interesting thing. Look at that. I didn't have to remember which port number it is for HTTP. I just asked for HTTP. It will resolve that to 80 for me. I could put something else. I could put the number there as well. If I failed to resolve, as usual, and if it worked, here you go. So I iterate over my list and use it. So all of my examples from this point forward will simply be looking at this use function. Well, at the end, remember to free and whatever. So let's look at what I do the other way around. So how do I resolve it back? So this is the example of taking an address info, right, and getting the host name back from it. So let me flip it, and we can look at it here. Get the name info of the addresses. I do not need the port number, and I get either the canonical name or the address. So the example you can see here on this, barely can see here, I asked for KMNet, right? And I got v4 and v6. I asked for Freenode, and I've got a bunch of v4 and now a couple of v6 at the end. Can anybody tell me why it showed v4 before v6? Look at the last one. It inverted the order. So I ran the first ones on a machine without IPv6. Or rather, it had IPv6, but it did not have global connectivity. So glibc detects that you do not have global connectivity. The IPv4 comes before v6. I will try these, and I will not waste time going on v6. When I connected to a different network that did have IPv6, now IPv6 came first. use getAddressInfo. So how do I connect to the host? Well, I'm going to use socket and then connect, right? So you're going to use socket and then connect. Let me just show on the bigger screen. Socket and then connect. Right. The rest here is just doing a get on HTTP. Now look at that. It gives me exactly what I need to connect. I do not need to do any casting. I do not need to do any guessing. Questions? Same thing if I were doing a server. So if I were doing bind. Remember the AI passive before? And I'm going to do bind with, so socket and bind, which is the exactly same thing. Now, what I said before about having v4 and v6 working together. By default on Linux, any IPv6 socket that you create and listen will accept connections from v4. So with one code base, with one file descriptor, you're accepting on both. Please do not try to write v4 and then add v6. Just do the v6 and you're serving everybody. The only detail is that the address you're going to get is like this. It's a v6 address with a v4 embedded in the middle, or at the end. So the only thing you might need to be careful is if you have like an ACL or a permission list for your clients, you might need to decode it. Now, if you do want to do, for some reason, you want to split it up, it can be changed. I showed the example here. Just make sure you were getting or not getting dual stack. Why I actually have setting it to on, even if it's default on Linux, I think on OpenBSD, it's not the default. They actually said that we don't want it by default. So I always turn it on. Yeah. Questions? Kind of running out of time, so just talking about things you can do with IPv6. Multicasting. One of the worst things you can do on IPv4 is broadcast. Broadcast is one to everyone. Remember, multicast is one to everybody in a group. Broadcasting is everyone in my network. Even those that are not interested in my packet, they will get it. And imagine powered devices on battery, devices powered on battery, they will be woken up to receive the packet even if they're not interested in it. So do not use broadcast anymore. You're going to use multicast. And this is the interesting thing. Because the address space is so large, you can create them without even consulting the assigned numbers on authority. The scopes there that I listed, the interesting ones are link local and realm local. More on the realm in a second. I can just send to the ones that are in my network, and I can ask the routers in my network to distribute it further to my site or my organization. Obviously, nobody does global multicasting. There are no routers that transmit global multicast, but could be used, for example, for streaming of TV, streaming of videos. This technology is there. It's not used right now, but could be used. So I just ask an address or assign it, and there are a bunch of RFCs I'm not going to go into detail of that would allow me to choose my own address, which is unique globally, but it's mine. I don't need to have to consult with the authority number. You can control your packets a little more. So this API from 3542 was created for IPv6. There are examples of it for v4. So most of these exist on Linux for v4, but they're not portable because there are no RFCs for other operating systems. So you can do this for v4, but it's slightly different on different OSs. So an example was, and CoAP, for example, requires you to do this. the packet that I received, was it sent to multicast address or was it sent to my non-multicast address? I need to detect whether I received via multicast or not. I want to send on a specific interface that also allows there. The API is a little cumbersome, but it's actually very, very powerful. And finally, 6LoWPAN, which is IPv6 over low-power wireless personal area networks. It's sitting on 802.15.4. The idea was IPv6 should work for everything, not just large devices and large networks. It should work for the smallest ones. So what they've done is that the radio interface basically maps to the IPv6 socket interface. I want to receive beacons, I just listen on multicast address. I want to send a beacon, I send a packet on a multicast address. I want to talk to somebody on the other radio that is in range of me, I send a packet to it because I know the IP address. The thread group goes and builds on top of this by creating a mesh. And this is where the realm local comes in, because I'm not just in radio range, I'm in my mesh network. I can send a packet which will get retransmitted by certain routers. More than that, they actually compress the header. So IPv6 headers can be as short as 3 or 4 bytes, which of course does not fit the entire address. That's because it actually does a stateful, interesting things between the sender and receivers. It also compresses the UDP header to as little as 1 byte. So now I'm sending a packet with IPv6 and UDP with 4, 5, 6 bytes header, which allows me to get the rest for my transmission. That is not the case on v4, that's not the case on TCP. If I'm doing those, I'm paying the full penalty of 20, 40 bytes. I do want to see if there's any questions left, so I'm going to stop here. There are a bunch of things I could talk to you about. I'm hoping that I convinced you to take this seriously. Any questions we have left? Okay, so thank you all for coming. You can contact me on email, on social media networks. I'm here all this today. Tomorrow I'm at the OCF event outside, but you can contact me anytime. Thank you very much for coming.